Chapter 7, Introduction to Sampling Distributions. In this video, we'll learn how to calculate the mean and standard deviation for the sampling distribution of a particular sample mean. We'll also talk about the importance of the central limit theorem. So hopefully you've already watched the bunnies and dragons video in our Chapter 7 resources before continuing on with this one. Recall in Chapter 2, we learned about frequency distributions, where we'll take the values of a particular distribution and we can graph the values to create a histogram. Similarly, when we're working with sampling distribution, this is where we are going to take the distribution of all possible values of a statistic, say the sample mean, for a given sample size that has been randomly selected from the population. In other words, if we took all of the possible random samples of a particular size and calculated the sample mean for each one and then graphed it into a histogram, we would get a sampling distribution. Now there are a number of theorems in this chapter that are going to help us work with sampling distributions. The first theorem is regarding the average value of our sample means. In other words, for any population, if I took all of our possible sample means and I calculated the average value of them, it's going to be the same as our population mean. Because if I'm studying every possible sample in a population, I'm essentially studying the entire population itself. We will write it as our mu of our sample means is the same as our population mean. Theorem 2 is known as the standard deviation of sample means, also known as the standard error. If I take all of my possible samples and I take their sample means, the standard deviation of these is population standard deviation divided by the square root of n. Theorem 3 states that if a population is normally distributed, that means it's bell-shaped, then our sampling distribution of our sample mean is also normally distributed, or also bell-shaped. And this allows us to apply Theorem 1 and Theorem 2 regarding our mean and our standard deviation of the sample means, or the standard error. Now in Theorem 4, which you watched a video on it regarding bunnies and dragons, for simple random samples of n observations taken from a population, regardless of the population's distribution, so regardless of whether it's normally distributed or if it's skewed or if it's bimodal, as long as the sample size is sufficiently large, then the distribution of our sample means is approximately normal, again allowing for Theorems 1 and 2 to apply. So regardless of what our population distribution shape is, if I were to pull every possible sample and calculate the sample mean for each, and then plot those values into a graph or a histogram, it's going to be normally distributed. It'll be bell-shaped. That's helpful to us because we know that if we're working with a bell-shaped curve, we can use Appendix D to find the probability of an event occurring. Note that the larger the sample size, the better the approximation to the normal distribution. So regarding the central limit theorem, this saves us a lot of time when we're trying to find the probability of an event. Regardless of what our population distribution shape is, it could be uniform, triangular, skewed. When we have a large enough sample size, our sampling distribution will be bell-shaped, and that allows us to use Appendix D for sampling distributions. Now some things to note about the central limit theorem. Our sample size must be sufficiently large. If the population is quite symmetric, then even small sample sizes like 2 or 3 can provide a normally distributed sampling distribution. We don't work with this too often though. If the population is highly skewed or irregularly shaped, such as bimodal, then the required sample size will be larger. Note that a conservative definition of a sufficiently large sample size is n will be greater or equal to 30. So thinking about our research projects with our Airbnb data, as long as you have more than 30 listings after you've cleaned and deleted any Airbnb listings you didn't want, we can use the central limit theorem when we want to calculate the probability of a particular event. In the last few chapters, we've been converting our x values into z values. Similarly, we can standardize our sampling distribution into z values. And recall, a z-value simply measures the number of standard deviations a particular value is from the mean. So here's our formula for our z-value, and it'll look familiar or very similar to what we learned in Chapter 6. Here we've got our sample mean minus our population mean, which is essentially our sampling error, and then we divide it by our standard error, or the standard deviation divided by our square root of n. This is the component that we learned about in Theorem 2. Now if we convert our value into a z-value, that means we can use Appendix D to find the probability of something happening. Let's look at problem 23 on our worksheet. Suppose a population is known to be normally distributed with a population mean of 2,000 and a population standard deviation of 230. If a random sample size of n equals 8 is selected, we're going to calculate the probability that the sample mean will exceed 2,100. So in step 1, we're going to identify our sample mean, where our sample mean we're examining is going to be 2,100. In step 2, we will define our sampling distribution thanks to our Theorems 1 and Theorem 2. Recall Theorem 1 states that if I take all my possible sample means and I calculate the average of them, it's the same as my population mean. Since we already know my population mean is 2,000, we have that for our Theorem 1. In Theorem 2, we are calculating the standard error, or the standard deviation of our sample means. So we'll take our population standard deviation of 230 and divide it by the square root of our sample size. In this case, it's 8. So when I take 230 divided by the square root of 8, we get a standard error of 81.32. Now keep note of these because you're going to need it for the next few steps. In step 3, we want to make sure we understand the event of interest that we're solving for. In this case, we want to know the probability that our sample mean will exceed 2,100. So we write the probability that our sample mean, or x bar, is greater than 2,100. And then in step 4, you'll go ahead and convert our sample mean to a z-value. So we take our sample mean of 2,100 minus our population mean of 2,000, and we'll divide it by our standard error that we calculated on the previous slide. So taking 2,100 minus 2,000 divided by 81.32, we can simplify where our sampling error is 100 in the numerator and our standard error of 81.32. Divide the two numbers and we get a z-value of 1.23. Now in step 5, we're just doing what we already learned how to do in Chapter 6, which is to read and use Appendix D to find our desired probability. Since I'm interested in finding the probability that my sample mean is greater than 2,100, it's helpful to draw my curve and mark where my z-value is of 1.23. And since I want to know greater than, I'm going to shade the area in the tail, because I'm greater than means I'm moving to the right of my z-value, or my 2,100. Recall that the appendix, when I read it, I'm going to look for the 1.2 in the left side under the z, and then I'm going to look for the column that says 0.03, or the second position of my decimal. The appendix, once we look up our 1.23, should give us a value of 0.3907 from our mean out to our z-value. But that's not the area I'm interested in. I'm interested in this shaded area, which represents the probability that our sample mean is greater than 2,100. Again, recall in Chapter 6, we know some things about this curve in that this half of the curve is worth 0.5. So if I know this half is worth 0.5, and according to my appendix, this piece of it is 0.3907, in order to get the shaded area, we'll have to subtract. So I'll take 0.5 minus 0.3907 from our appendix, and the probability of our shaded area is 0.1093, or 10.93% chance that our sample mean will be greater than 2,100. So as you can see, finding our mean and standard deviation and the probability of an event of our sampling distribution is a combination of several things that we've learned about in our previous chapters. If you have any questions, just let me know.